Ladies and gentlemen, good evening. We invariably gaze upwards at the night sky, confronting the profound abyss of the universe enveloped in silence. Within that vast darkness, stars emit their individual lights like isolated islands, separated solely by the absolute barriers of time and distance. Since humanity first attained intellect, we have persistently posed questions. Is there truly no method to transcend this immense solitude of the cosmos? How might we communicate with those distant stars, where even light requires tens of thousands of years to arrive? Today, we venture into the most peculiar and captivating domain reached by modern physics, the realm of quantum mechanics. In particular, we shall discuss quantum entanglement, the phenomenon that Einstein termed a spooky action at a distance and so ardently wished to refute. We shall explore deeply whether this phenomenon could serve as the key to the interstellar communication humanity has dreamt of, and whether the reality we perceive is indeed a fixed entity. Our discussion today originates from a highly intriguing question submitted by Chien Lok. The query posits, might the phenomenon of quantum entanglement enable instantaneous communication between stars, disregarding the universal speed limit imposed by the velocity of light? This extends beyond mere individual curiosity. It represents one of the most fundamental inquiries confronting contemporary science. To state the conclusion forthwith, the answer is presently no, or at least impossible in the foreseeable future. Theoretically, two quantum particles influence each other's states instantaneously, unbound by constraints of distance and time. However, the interaction of states and the transmission of information constitute distinctly separate dimensions. To comprehend this subtle yet decisive distinction, we must embark on a journey into the deepest recesses of matter. First, it is essential to define clearly the essence of the phenomenon known as quantum entanglement. Many individuals confuse quantum superposition with quantum entanglement. Superposition refers to a single particle existing in multiple states simultaneously prior to observation. In contrast, entanglement signifies a state where two or more particles share a destiny, as if connected by an invisible thread. These particles function as a single system, even if separated across opposite sides of the universe. How, then, are such entangled photons produced? Scientists employ exceedingly precise and delicate methods for this purpose. The most representative approach involves splitting a photon into two, though this differs fundamentally from slicing an apple with a knife. In physical terms, this is termed spontaneous parametric downconversion. To understand this process, we must delve into the internal structure of matter, particularly the orderly arrangement of atoms within what are called crystals. Scientists direct a high-energy laser onto a special nonlinear crystal. The term nonlinear is pivotal here. In ordinary linear crystals, the vibrations of electrons respond proportionally to the electric field of the light, akin to a supple spring. Weak light induces weak vibrations, strong light induces strong ones, allowing the light to pass unaltered. However, the realm of nonlinear crystals is different. Here, electrons react asymmetrically to external stimuli. An electron is pulled more forcefully in one direction, disrupting the balance of restorative forces. Within this distorted vibration, peculiar quantum effects emerge. A single photon of high energy, upon traversing this nonlinear medium, disintegrates, splitting into two photons of lower energy. The two photons thus born precisely divide the energy of their parent photon. The laws of energy conservation and momentum conservation remain absolute sovereigns even in the quantum world. Crucially, these two photons are entangled from the moment of their birth. This arises not from collision. Had the photon collided with an electron, the electron would have been ejected from the atom. Nor is it a process of absorption and re-emission by an atom, which occurs with a time delay and precludes simultaneous emission of two photons. For entanglement to hold, the two photons must emerge perfectly simultaneously, without temporal discrepancy. The probability of this is exceedingly rare, approximately 1 in a billion. Thus, one must dispatch a billion photons to yield merely one entangled pair. Scientists utilize wavelength filters to identify these precious twins. If the parent photon's wavelength was 400 nanometers, the newborn twins must each possess a wavelength of 800 nanometers. Recent advancements have refined this process further. For instance, in 2025, researchers at Stanford University developed a room-temperature quantum communication device that entangles photons and electrons using twisted light from molybdenum diselenide, eliminating the need for extreme cooling and enhancing practicality for broader applications. This breakthrough stabilizes quantum states, potentially increasing the efficiency of generating entangled pairs beyond traditional cryogenic methods. We now confront the monumental engineering challenge of transmitting these laboriously obtained entangled photons. Quantum states are as fragile as glass beads. Collisions with their molecules, temperature fluctuations, or even minute vibrations can sever the entanglement. The journey of a photon across 143 kilometers from La Palma to Tenerife in the Canary Islands in 2012 was nothing short of miraculous. Subsequently, China's MISHAS satellite conquered a distance of 1,200 kilometers by dispatching entangled photons from orbital space to ground stations. In a more recent feat, the Jinan 1 microsatellite in 2025 established a quantum link spanning 12,900 kilometers between China and South Africa, demonstrating the feasibility of uplink quantum entanglement distribution from Earth to satellites and paving the way for robust quantum networks. Yet, terrestrial transmission, particularly via optical fibers, encounters another despairing obstacle. Light traversing optical fibers weakens dramatically with distance. After 100 kilometers, 99% of photons vanish. Conventional internet signals revive through amplifiers, replicating and amplifying weakened signals for onward transmission. However, quantum information adheres to the no-cloning theorem, rendering replication impossible. Attempts to amplify constitute observation, thereby destroying the entanglement. Thus, quantum communication demands a solitary battle without relays. The record of 12,900 kilometers between China and South Africa was not mere communication but a triumph of engineering, achieved through precise alignment akin to threading a needle between satellites and ground stations. To surmount Earth's curvature and topographical limitations, scientists have devised the profound technique of entanglement swapping. This magically entangles photons at 2 points that have never encountered each other, utilizing an intermediary relay. When Alice sends a photon to Bob and Bob to Charlie, Bob performs a special observation known as a Bell measurement on his 2 photons. At that instant, the entanglement of Bob's photons fractures, but the repercussion entangles Alice's and Charlie's photons. Spatially separated particles connect via a mediator. Yet, this necessitates quantum memory technology to temporarily confine photons. Since light does not halt, techniques imprison it within clouds of atoms such as rubidium or cesium, storing information as spin waves, a pinnacle of modern physics. Advances in quantum memory continue to evolve. For example, in 2025, scientists at Fermilab and Caltech demonstrated the use of squeezed light, a state with reduced noise, to enhance the generation rate of entangled pairs over long distances. Combining optical encodings to overcome individual weaknesses and accelerate progress towards large-scale quantum networks. Might piercing all these technical barriers with connected quantum entanglement enable communication faster than light? Here, we encounter the epochal debate between Einstein and Bohr, and the philosophical turning point of Bell's inequality. Einstein believed that God does not play dice. He posited that entangled particles possess predetermined hidden variables unbeknownst to us. Akin to dividing a pair of gloves into boxes and dispatching them, opening one reveals the other's nature instantaneously, yet the information was predetermined. This is local realism. However, John Stuart Bell presented a mathematical inequality to test this hypothesis. Numerous experiments have proven Einstein erroneous. No predetermined hidden variables exist in the quantum world. A photon's polarization state remains undecided until observation. At the moment of observation, reality emerges. If Alice measures her photon and obtains vertical polarization, Bob's photon, across the universe, instantaneously determines as horizontal. This is not information traversing but the simultaneous collapse of their shared probability wave. A 2025 study from the Technion Israel Institute of Technology revealed a new form of quantum entanglement in the total angular momentum of photons confined in nanoscale structures, extending beyond conventional properties like spin or trajectory, and opening avenues for hidden quantum communication. At this juncture, the impossibility of communication is demonstrated. Alice cannot predict or control her measurement outcome. It is randomly determined by nature's probability. She cannot convey her intent to Bob as 1 or 0. Bob, too, cannot discern whether his result stems from Alice's measurement or his own. Only later, via classical means like telephone or email, slower than light, can they compare results to confirm correlation. Without accompanying classical communication slower than light, quantum entanglement alone conveys no meaningful information. Is this bizarre phenomenon then useless? Far from it. Humanity harnesses this randomness to forge unbreakable security systems, quantum key distribution. Alice and Bob share entangled photons, each randomly setting polarization angles for measurement. Subsequently, via public channels, they compare angles alone. Where angles match, their results correlate perfectly. This sequence forms their exclusive secret key, a random number table. This key's strength lies in the fundamental impossibility of eavesdropping. If an interloper intercepts and measures a photon, the entanglement shatters, altering the quantum state. Alice and Bob detect this via error rate checks. No supercomputer, however advanced, can violate physical laws. The message travels classically, but its lock is safeguarded by the universe's foundational principles. This explains why nations, including Korea, stake their futures on quantum cryptography. According to a 2025 McKinsey report, the quantum communication market, valued at $1.2 billion in 2024, is projected to reach between $10.5 and $14.9 billion by 2035, reflecting a compound annual growth rate of 22 to 25%. In 2025, Kyoto University scientists unlocked the identification of the elusive W state in 3-photon entanglement, resolving a decades-old challenge and enabling advancements in quantum teleportation, multiphoton state transfer, and measurement-based quantum computing. Additionally, Virginia Tech's ECOMAL framework leverages entangled qubits for enhanced communication in disaster relief scenarios, such as wildfire fighting drones, surpassing classical and non-entangled quantum methods. Scientists now challenge beyond mere communication towards quantum memory and repeaters. Light's incessant motion hinders storage, but cooling rubidium or cesium atomic clouds near absolute zero allows entangled photons to transfer states into spin waves, effectively imprisoning light as information within matter. A subsequent laser pulse retrieves it as light. This magic, akin to bottling light, forms a crucial bridgehead for future quantum internets. In conclusion, quantum entanglement does not permit us to exchange greetings faster than light. The universe, through the stringent law of causality, forbids the past from overtaking the future. Yet, this phenomenon imparts a deeper truth: the world we observe is not a solid entity existing independently of observation, and all things in the universe may be profoundly interconnected in unseen dimensions. We have merely gathered a few pebbles from the shoreline of the vast quantum ocean. Though entanglement-enabled communication transcends light speed remains impossible, the era of quantum information science it has unveiled is just commencing. Perhaps, in a distant future, we shall surpass spatio-temporal constraints in ways beyond our current imagination. Until then, we must humbly attune our ears to nature's subtle whispers. Science is not a process of finding answers but an endless journey of erasing our ignorance one piece at a time. That concludes the narrative prepared for today. I hope it has aided, even slightly, in understanding the intricate and beautiful world of quantum mechanics. Thank you for exploring the mysteries of the universe with me over this extended period. I shall return next time with an even more profound topic. Farewell. Ladies and gentlemen, good evening. We gaze upon the night sky, confronting stars immersed in eons of silence. Within that expansive darkness, humanity has always sensed loneliness and yearned to reach someone, or perhaps our future selves, across the distant cosmos. Before this despairing distance, where light itself demands tens of thousands of years, we dream of a miracle that transcends space and time, mocking the universal speed limit set by Einstein. That is the phenomenon of quantum entanglement. Might this ghostly remote action usher us into an era of interstellar communication? Today, we set sail into the deepest abyss of science, the strange and beautiful quantum sea. before debating whether the instantaneous information transfer we imagine as telepathy is physically feasible, we must first unearth the primordial secret of how the starring actors in this peculiar phenomenon, the entangled photons, are born. Entanglement does not arise merely by flicking a switch in a laboratory. It is an exquisite art wrought by nature's symmetry and conservation laws. Scientists perform a highly complex and delicate process termed spontaneous parametric downconversion to create these special twins. At the heart of this process lies a special stage, the nonlinear crystal. Crystals such as beta barium borate or potassium titanyl phosphate feature electrons arranged in uniquely distinctive ways within atoms. In linear media like ordinary glass or water, electrons vibrate in direct proportion to the light's electric field, like a pliant spring. Gentle pushes yield gentle sways, forceful ones yield forceful, without altering the light's essential color or frequency. However, the nonlinear crystal's realm differs. Here, electrons resemble taut rubber bands or asymmetrical springs. When a potent laser, the pump photon, impinges, they cannot endure the energy, distorting vibrations with an eerie cry. In this nonlinear distortion's instant, magic transpires. A single high-energy violet laser photon interacts fiercely with the electron cloud within the crystal, annihilating and birthing in its stead two red photons of precisely halved energy. This is the progeny of energy and momentum conservation laws meeting quantum probabilities. These newborns, dubbed Signal and Idler, share spacetime from birth, forging a fateful entanglement. If one vibrates vertically, the other must horizontally, a perfect correlation permitted by the universe. Yet, this process is profoundly inefficient. Billions of photons flood the crystal, yet only one pair emerges entangled, like finding a single pearl in a vast sandy beach. Scientists employ precise filters and prisms to distinguish these rare twins by wavelengths exactly double the incident lasers, and nanosecond precision timing devices acknowledge only those arriving simultaneously at detectors as genuine entangled pairs. A 2025 discovery by SpinQ researchers identified a new type of quantum entanglement without requiring identical particles, confirmed via interference patterns, expanding tests of quantum non-locality into novel regimes. Transmitting these arduously acquired entangled photons afar presents another dimension of challenge. Atmosphere scatters light, optical fibers absorb it. The aforementioned 2012 Canary Islands experiment and 2017 MISSION satellite endeavor were not simple communications but victories of precision engineering amid Earth's rotation and orbital motion. Targeting meter-scale ground telescopes with invisible single photons over hundreds of kilometers. Optical fiber transmission collides with the colossal wall of loss. Modern optical networks replicate and amplify waning signals via amplifiers. Yet, the quantum realm's no-cloning theorem reigns supreme. Attempting replication is observation, chattering entanglement. Thus, quantum communication treads a precarious path, delivering originals unamplified to destinations. Might two photons, connected after surmounting all obstacles, enable faster-than-light communication? Here, we revisit 20th century physics' grandest contest, Einstein versus Niels Bohr, and John Stuart Bell's inequality. Einstein believed God does not play dice, asserting that particles appearing to react instantaneously across distances possess hidden variables predetermined at birth. To illustrate simply, consider the glove paradox. Suppose a pair of gloves is divided left and right into boxes, sent to Alice and Bob on opposite Earth sides. Alice opening hers and confirming left instantaneously ascertains Bob's as right. Is this information transfer? No. The gloves were predetermined left and right, merely unconfirmed. Einstein viewed quantum mechanics similarly, reality predetermined before measurement, advocating local realism. Yet, the Copenhagen interpretation differed. They contended that until the box opens, the glove exists in neither left nor right but a probabilistic superposition of both. Observation collapses the wave function spanning the universe, determining reality. John Stuart Bell elevated this philosophical dispute to experimental scrutiny, mathematically proving that if hidden variables exist, correlations must satisfy Bell's inequality, a statistical limit. Scientists twisted photon polarization angles in experiments to test this. If states are predetermined, probabilities of matches or mismatches when Alice and Bob rotate polarizers at angles like 0 degrees, 22.5 degrees, 45 degrees cannot exceed classical intuition's bounds. Calculations yield clear thresholds. Yet, results shocked, correlations at subtle angles, especially 22.5 degrees, blatantly violated Bell's inequality. Einstein was wrong. No hidden variables, particles undecided until observed, sharing one wave function. Alice's measurement instantaneously prompts Bob's state determination, a proof of non-locality, fundamental connection despite spatial separation. A 2025 study published in Annals of Physics proposed that quantum entanglement entropy-shaped spacetime, reformulating Einstein's field equations to unify gravity and quantum mechanics. Suggesting gravity responds not only to mass and energy but to quantum information structures. Many excite at this point, might Alice manipulate her particle to signal Bob instantaneously? Yet, nature erects another barrier, randomness, to safeguard causality. Alice cannot select her measurement outcome, vertical or horizontal, it is 50-50 by nature's probability. She is merely an observer casting dice. From Bob's perspective, his result's origin, Alice's measurement or his own randomness, remains indistinguishable. Individually, their data are perfect random number tables. Only post hoc, via light-slower classical means like telephone or internet, can they align results to confirm entanglement. Information never exceeds light speed. Entanglement certifies correlation between points, not a truck hauling information. Is this peculiar phenomenon then valueless as a communication tool? Paradoxically, its uncontrollable randomness and collapse upon observation gift humanity unbreakable security, quantum key distribution. This secures information impeccably, not transmitting swiftly. The principle is exquisite. Alice and Bob share entangled photons, each randomly setting polarizer angles for measurement. Crucially, not the values, 0 or 1, but angles matter. Post-measurement, via public channels, they query, what angle did you use? 0 degrees. Me too. Matching angles yield perfectly correlated results per quantum principles. Mismatched data discard. Filtered sequences form their shared perfect random key. This key's potency, eavesdropping impossible at source. If Eve intercepts and measures, entanglement fractures, quantum state alters. Eve covertly measuring and resending yields contaminated photons. Alice and Bob detect via error rate contrasts in public data subsets, someone listened. They discard, regenerate. No supercomputer hacks physical laws. Messages travel classically, locks protected by universal fundamentals. Combined with one-time pad, quantum cryptography is theoretically undecipherable. Furthermore, the space entanglement and annealing quantum experiment in 2025 aims to demonstrate space-based quantum communication with entangled photons, advancing scalable quantum networks and global infrastructure. Aliro Quantum's 2025 predictions highlight quantum networking error correction reducing qubit error rates, enhancing key generation at lower costs, and fostering new repeater designs for extended distances. In conclusion, quantum entanglement does not allow faster-than-light greetings. The universe's causal law prevents results preceding causes or information-defying time's flow. Real-time dialogue with Andromeda Galaxy friends remains impossible. We must endure the silence of that distance as cosmic providence. Yet, no need for despair. This phenomenon reveals deeper, wondrous truths. Our world is no assembly of independent fragments. All cosmic entities entwine deeply in unseen dimensions. Observation births reality. We are not isolated islands but connected existences atop a vast quantum wave ocean. We have merely gathered pebbles from the quantum ocean's shore. Though superluminal entanglement communication remains impossible, the quantum information science era it inaugurates dawns. Perhaps distant futures transcend spatio-temporal limits unimaginably, or unveil unknown cosmic layers. Until then, humbly attune to nature's subtle whispers. Science is no period-affirming answers but endless question marks erasing ignorance. That concludes today's narrative. I hope it has aided, even slightly, in comprehending quantum mechanics' intricate, beautiful world and its hidden connection mysteries. Thank you for delving the cosmic abyss with me over this extended time. I shall return next with a deeper, more captivating topic. Farewell. Ladies and gentlemen, thus far we have raced breathlessly through quantum entanglement's bizarre phenomena, its quantum cryptography applications, and quantum memory's technological frontier. Yet, at these scientific achievements and progress's terminus, we must pause to confront the true direction this phenomenon indicates, the fundamental philosophical quandary the universe poses us. Our inhabiting universe appears a space of thorough solitude and disconnection. Distances demanding light tens of thousands of years impose overwhelming silence upon stars. Einstein's cherished causality and locality principles perhaps serve as minimal order and safeguards preventing individual existences from invading each other's realms in this vast cosmos. Incapable of faster-than-light communication, we fully own our times and spaces. However, quantum entanglement exposes the fervent connectivity hidden behind that cold order. Though information cannot surpass light speed, existence's essential states mock spatio-temporal constraints in entanglement. This casts truly wondrous implications. 138 billion years ago, at the universe's primordial point, all matter and energy were one. Now, in expanding cosmos, scattered into galaxies, stars, you and I, but from quantum mechanics' vista, we may yet linger in that initial embrace. Gazing at others or night sky stars is not viewing unrelated strangers. It mirrors another self, momentarily separated in spacetime's grand illusion. Quantum mechanics intimates the universe as no mechanical assembly of independent parts but a singular vast organism breathing organically. That my observation determines a cosmic distant state proves we are no mere spectators but active participants creating the universe. Science has merely lifted the hem of that grand truth. What we term randomness may be higher dimensional order we yet comprehend not, uncertainty, another name for universe's infinite possibilities. With this incomplete knowledge, we harness natural laws to lock information and confine light. Yet, as technology advances, we must grow humbler. Brighter revealed light deepens and thickens surrounding unknown darkness. Ultimately, quantum entanglement's final message is connection and humility. We are no isolated islands, we touch deeply in unseen dimensions. The universe silences not but whispers incessantly in quantum language we yet fully comprehend. Attuning to that whisper is the path humanity must tread in science and philosophy. I hope the story we shared today ripples small waves in your worldviews. May those waves propagate, becoming new entanglements comprehending the vast cosmic mystery. Thank you profoundly for exploring the cosmic abyss with me over this extended time. I shall return next with a deeper, more captivating topic. Farewell.